Good morning. Today we're going to go over lesson 34, which will get into the Gram-Schmidt orthogonalization process. So let's review some of the ideas that we've been focusing on over the last few lessons. So for today, I want to fix two ideas. Let's fix either our field F as the real numbers or the complex numbers. And let's let V be a finite dimensional vector space. So there were two concepts that we've been focusing on recently. The first is the concept of an inner product. So remember that a map, and here we're using our angle brackets, this is something that takes two vectors to a complex number C, so our complex number in C, is said to be an inner product if the following hold. For all vectors x, y, z, and v, and all scalars, in this case, little c. So the first we need is this idea of linearity. So what I mean by that is if we take this linear combination, cx plus z, then we can expand that out as the following. Number two, we have the idea of symmetry. So what I mean by that is this. Because this inner product, this angle bracket xy, is in the complex numbers, I can consider its complex conjugate. And the statement is that all I have to do is just reverse the two arguments. Third, we have positivity. And that says that the inner product of a vector with itself is a non-negative number. And the final one we have here is non-degeneracy. So what I mean here is the inner product of x with itself is 0 as a complex number if and only if x itself is the 0 element from our vector space V. Now remember that there are lots and lots of inner products. So here I'll just write one. Let's say that V is Fn. You can either think of this as the collection of n tuples over the real numbers or n tuples over the complex numbers. Doesn't really matter. And let's choose n positive real numbers. Now we can define a map by simply doing this. So here I will take the first component of our vector x, the complex conjugate of the first component of our vector y, and then I'll multiply that by this real number r1. And I will do this for each and every one of the components. So the statement is that this is an example of an inner product on V. In particular, if each of our positive real numbers here is equal to the number 1, we call this the standard inner product. So again, we have the concept of an inner product as a very general idea, and then here we'll just focus on this specific standard inner product. But let's still try to write down slightly more general definitions here. Let's fix an inner product on our vector space V. Now I want to remind you, what does it mean to be an orthonormal basis? Well, a subset, which we'll write here as beta, perhaps it has the elements V1 through Vn. And again, this is an orthonormal basis. If 4 things hold true. So first, we have to know that it spans V. So what I mean by that is, given any, say perhaps x in V, there exist scalars such that x here can be written as a linear combination of the elements in beta. Right, so simply put, beta spans V. Number 2, we want the set to be linearly independent. So what I mean by that is that the only scalars satisfying the following equation. So that is here what we want is a1 v1 plus a2 v2 plus a n vn equals 0. Of course, this is the element of our vector space V. And the only scalars that are possible here better be the 0 scalar. So again, this is what it means to be a linearly independent set. Third, I want orthogonality So what I mean by that is for our indices I different from j, then the inner product of vi and vj should be 0 as a complex number. And then finally, I want to make sure that this set beta is normalized. So what I mean by that is, say for instance for each I, then we have now the length of VI, which remember is just defined as, I'll take the inner product of VI with itself, and then we'll take the square root of that. So this here should be 1. So again, if our set beta satisfies these 4 properties, then we'll say that beta is an orthonormal basis. So let's quickly review some examples here. Let's say that V is F2, and our inner product is the standard inner product. Then in this case, we actually found that there's lots of examples. So here, let's fix 2 real numbers, not both 0. And an example here that would work would be a equals 1 and b equals 0. So again, pick whatever your favorite real numbers are that are not both 0. And let's consider these vectors. So V1 here, we'll let be this vector. So here I'm taking a divided by the square root of the sums of a squared plus b squared, and then b divided by the square root of a squared plus b squared. And we'll do something similar here with V2. So this will be negative b divided by the square root of a squared plus b squared, and then finally a divided by the square root of a squared plus b squared. So the claim is that this is an orthonormal basis for V. And of course, the main thing to note here is that there are infinitely many orthonormal bases for V. Right? It's not just one. There are infinitely many. So you have to decide which one. Now, here's really the goal for the day. What we'd like to do is always write down a very nice basis for V. So I'll write it this way. Given such a vector space V along with an inner product we want to explain why there is always an orthonormal basis. In fact, I'm going to go even stronger than that. Let's say perhaps that we have any spanning set S. So of course what I mean by that is V is the span of S. So maybe it's not quite a basis. Remember that a basis means that it spans this and that it's a linearly independent set. So let's not even assume that it's a linearly independent set, just that it spans the vector space. Then what we want to do is we will present an algorithm to construct from this spanning set an orthonormal basis beta. So really, this is going to be our idea for today, is that I want to present a series of steps so that if someone gives you S, you can construct a very nice orthonormal basis. Right. So here are the three big theorems for the day. So this whole process is actually what's called the Gram-Schmidt orthogonalization process. So as you can probably tell, orthogonalization means it's the process by which I will make something orthogonal. So all of this will be contained in these theorems 6.3, 6.4, and 6.5. Right. So just like before, let's say that we have an inner product on a vector space. That's defined over a field F. And it doesn't matter if I assume that my ground field is the collection of real numbers or the collection of complex numbers. Everything that I'll say here will work in either case. So there's three statements that I want to make here. The first is, let's say that W is the span of a linearly independent subset and let's perhaps write these elements as W1 through W sub k. So that is, I have a subspace W, and let's say that S here is a basis for W, right? It spans W, and it's a linearly independent set. So it's a basis for W. Let me define a new set. So I will call this S prime in terms of these vectors V. And I'll define them as follows. My VI's will be defined recursively in the following way. The first one will be W1. And the rest will be defined in this weird way here. So I'll take WI, but now I'm going to subtract off these previous vectors. So it should be WI VJ divided by the length of VJ squared times VJ. So again, here, if I want to compute the ith vector Vi, when I is 1, I'll just pick the first vector, Wi, right? The first vector from my set S. Next, I don't quite want Wi in general, but I'm going to subtract off this scalar times this vector Vj. Now this scalar says in the numerator, I want Wi inner product with Vj. And in the denominator, I want the length of Vj squared. Remember that the length of Vj really is going to be related by this here. So it just means the square root of the inner product here, Vj with itself. So I can really write the denominator in terms of the inner product if I wanted to. So of course we'll give some examples of this, but again, all that I'm saying here is that if I want to compute, say, V1, it's W1. If I want to compute V2, it would look like W2 minus a certain scalar times V1. Now if I want to compute V3, it will be W2 minus some scalar times V1 and then minus another scalar times V2. So this is what I mean that I can kind of do this recursively. So then the statement is S prime is an orthogonal set of vectors which spans W. What I mean by that is if I were to take the inner product of Vi and Vj, then this is 0. Of course, when I is different from j. And W is the span of S prime. Right, so this weird construction here allows me to take any basis that I have for a subspace W, right? It spans it and it's a linearly independent set, and it turns it into now an orthogonal basis, right? So it's a basis, so it spans it, it's a linearly independent set, but now everything is orthogonal. And let's go one step further. Next, let's say maybe that we've already computed some kind of an orthogonal basis. So let's say that W is the span of an orthogonal subset. And let's call this S prime, again, maybe in terms of these V's here. Right, so before, it was just the span of a set, some linearly independent set S. Now I'm playing around with it a little bit, and I'm going to say, let's say that it's the span of an orthogonal set. Then the statement is S prime really is a basis. Right? That is, S prime is actually a linearly independent set. Moreover, each element can be expressed in the following form. So here I have a sum. I goes from 1 to k. Now the whole point before I write this down is to say that saying that S prime is a linearly independent set is one thing, but if I know that it's the span of something, S prime spans W, then that means everything in W can be written as a linear combination of these here. Well, what this actually says is I know a lot about these coefficients. So this here says that I have a scalar times this vector vi. So this actually gives me a nice formula for finding what are these coefficients if I had a linear combination. All right, so we'll come back to this a little bit later. Okay, so again, S prime here, if it's an orthogonal spanning set, then it actually has to be a linearly independent set, so it has to be a basis. And moreover, because it is the span of an orthogonal set, then everything in this W prime inside of the space W can be written in a very nice explicit way. So again, I know exactly what these scalars are for expressing this. Okay, so here's the third property. Now, let's let W in terms of S double prime be the span of an orthonormal set. And let's maybe write these elements here in terms of U's. And just to remind you, orthonormal means that it's orthogonal and normalized. So S prime is a special case of S double prime is a special case of S prime. Right? S prime just means everything is orthogonal. We know that it has to be a basis. It's a linearly independent set. So if it's the span of an orthonormal set, then again, everything here has to be a linearly independent set. So this formula actually simplifies quite a bit. So the statement is, first of all, S double prime is a basis for W, and each Y in W can be expressed uniquely as the following linear combination. So I'm going to write almost the same thing as what I wrote over here to the left, but now I don't have to worry about a denominator. So again, these here are scalars. But I don't have to worry about this absolute value of ui squared because it's normalized. So again, let's try to recap what this proposition, what these theorems here actually say. So let's say that you have an inner product. So just fix your favorite inner product over your vector space. And let's start with something that's the span of a linearly independent set. Let's call this S prime. Then I can do this trick here, and I can find this S prime that now is an orthogonal set. And the next statement is that this orthogonal set actually is a basis. It's actually another linearly independent set. And so I can use that to say that there's a nice formula for expressing every element as a linear combination of the elements from S prime. It's really just this formula here. And in the specific case that we're dealing with an orthonormal set, then actually here we have a really nice simple formula. So let me perhaps make this quick comment. You'll see that if we have an orthonormal basis, we really need to know these four properties here. So that is span, linear independence, and orthogonality. It turns out that you actually don't need this condition here of linear independence, because if I know that it spans the set, and if I have a collection of orthogonal vectors, right, so these two here, this is what I'm calling here as the set S prime, automatically that set is a linearly independent set. So the point is that really these two properties here force the set here to be a linear independent set. And actually, because it's a span, it forces it to be a basis. So again, I actually don't need all four properties. I really just need 3 of these 4, and then I get back this one here for free. Right. So with this proposition, I really want to ask the following question. So I'll write this here as a remark. Let's say that W is the span of some set S. So that is, let's say that our S here, in terms of these W's, say that this is a basis for a subspace W. I will perform the following steps to find an orthonormal basis for W. And let's call this perhaps S double prime, which I'll write here in terms of these U's. Right, so again, say that we're just given a basis, and now I want to do some process to find an orthonormal basis. So the first thing we'll do is let's try to construct an intermediate basis which let's call this S prime in terms of these V's. Right, intermediate just means it's going to be temporary, so we can kind of get our formulas to work out. And the intermediate basis here, this VI, will be exactly what I wrote over here on the right-hand side. So either we'll start with the W1 for I is equal to 1, or we'll take WI, but then I'm going to subtract off this J goes from 1 to I minus 1, and we'll have here this ratio. So this is WI inner product with VJ divided by inner product Vj with itself. And this will be for I greater. Right? So this is just a nice recursive formula. And remember that this here is a scalar times this vector. And again, we'll do some examples of this in just a minute. Number 2, we'll now construct S double prime by letting our U sub I be 1 over the norm of VI times VI. So we really have to do these 2 processes. So of course we start with our set S, that's in terms of these W's. Next we want to construct this intermediate basis. This means that this is an orthogonal set by doing this weird process here. So I have to subtract off the scalar multiple of the previous VJs. And then third, I have to construct these U sub i's by dividing by the length or the norm of VI. So you really have to do all 3 of these together to get this to work. Right. So of course, this whole thing here, this process, is what's called the Gram-Schmidt orthogonalization process. So again, the process says if you start with a basis, call it S for some subspace, the process by which you construct an orthonormal basis is exactly this here. First, you construct an orthogonal basis. This is this S prime by this. Then you normalize that basis by dividing by the norms here. So let's perhaps work a few examples of this. So I'm going to skip over a couple of the more abstract examples from the lecture notes, and I'll go right to the end and try to do this very concrete example that has specific numbers. So let's say that V here is R4. And let's consider, let's say, the standard inner product. Right, so of course what I mean by the standard inner product is it's exactly what you expect. Here I'll just take the sums of these products. And of course I could put complex conjugates here. It doesn't really matter because I'm dealing with the real numbers. I could just deal with the complex numbers. It really doesn't matter very much. Now let's let W be the span of this here, where S will be the set consisting of these three elements. And let's just explicitly write out the three elements over here. W1 here will be this 4 tuple, 1, 0, 1, 0. W2 will be this 4 tuple, 1, 1, 1, 1. And W3 will be this 4 tuple, 0, 1, 2, 1. So I won't worry about proving this, but this here is a linearly independent set. So again, S here is the basis for W. So what I'd like to do is construct an orthonormal basis for W. So here's how we'll do this. First of all, we need to go through this process here and construct an orthogonal basis. And let's call this basis S prime, which will consist of V1, V2, V3. All right, so again, first let's do this, and then afterwards we'll make this normalized. So now let's start just by writing out what the formulas tell us. So we know that V1 is supposed to be W1. Right? That's what this formula here says. So take the first one just to be the first vector here. Don't even think about it. So in this case here, it's just 1, 0, 1, 0. Okay, so we're 1/3 of the way done. For V2, we need to do this trick here. So I have to take W2 and then subtract off something. So again, I need W2. And then I'm going to subtract off Here I need the inner product of W2 and V1 divided by the inner product of V1 and V1. Right, so again, the inner product of W2 and V1 divided by the inner product of V1 and V1, all of that scalar times our vector V1. Right, so this is the definition of V2. So now, of course, we need to do a little bit of algebra to work some things out here. So first, let's start with W2. So according to this, that's just 1, 1, 1, 1. Minus, now let's take a look at the numerator here. W2 was 1, 1, 1, 1, and I need to take the inner product with V1. So according to this definition up here, I have to take the first row of W2, times the first row of V1, right, this times this. Now I take the second row of W2 times the second row of V1, so 1 times 0. Now I take the third row of W2 times the third row of V1, so 1 times 1. And finally, I take the fourth row of W2 times the fourth row of V1, so that's 1 times 0. So again, this is how we compute the inner product of W2 and V1. That I have to take a look at the different rows, and then I sum over everything. Now for V1, all that I really am doing is just looking at the sums of the squares. So here I would have a 1 squared plus a 0 squared plus a 1 squared plus a 0 squared. Right, so again, that's the denominator here. And finally, I multiply by the vector V1, which in this case was just 1, 0, 1, 0. Right? So if we put all of this together, then of course here for the numerator, I would have 2 divided by 2. Right? So just 1 plus 0 plus 1 plus 0, 1 plus 0, 1, 0. So this here is just the number 1. So here I would just take 1 minus 1 will be 0. 1 minus 0 is 1. 1 minus 1 is 0. And then 1 minus 0 is 1. Right. Okay, so this is my vector V2. Now, as a sanity check, we really should get that the inner product of V1 and V2 is 0. Right, so I won't worry about proving that here on the board, but you can just check if you've done this right, then this inner product with V1 and V2 better be 0. Okay, let's keep going. So what about V3? So according to this definition, I want W3, but then I have to subtract off different things. So here we'll have W3. Now I have to subtract off this scalar times V1. So this will be W3, V1, V1, V1. Right, so again, the inner product of W3, V1, divided by the inner product of V1 and itself, times the vector V1. Now we have to subtract off the case when j is equal to 2. So W3, V2, 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 multiplied by the vector V2. So W3, V2, divided by V2, V2 times V2. Okay, so let's try to substitute some things here. So for V3, I'm just going to substitute back what I had as what was given. So 0, 1, 2, 1. Minus, now let's try to compute the inner product here. So I have to take a look at, say, the different rows here for W3. So let's maybe just write that in here. And then I have to take a look at the rows of V1. So 1, 0, 1, 0. So I'll write that in here. 1, 0, 1, 0. Right, so again, here I have a 0, 1, 2, 1 for W3. And then I have a 1, 0, 1, 0 for V1. Now I have to divide by the squares for v1. Again, multiply by v1. Well, v1 we said was this here. We'll have to do something similar here for v2. So first let's put in what we have for w3. And now let's put in what we have for v2. In this case, v2 was 0, 1, 0, 1. So here I'll put in 0, 1, 0, 1. So again, I have 0, 1, 2, 1 corresponding to w3. And then I'll put in 0, 1, 0, 1 corresponding to v2. And here in the denominator, I just have to have the sums of the squares 0, 1, 0, 1. And I'll put in here v2. 0, 1, 0, 1. Right? So now I have to simplify this. Okay. So before, of course, we know that this here just cancels out to 1. Over here, we'll have 0 plus 0 plus 2 plus 0 divided by 1 plus 0 plus 1 plus 0. So really this here also simplifies to 1. And over here we have a 0 plus 1 plus 0 plus 1, and then 0, 1, 0, 1. So this also simplifies to 1. Right, so these ratios here are actually very nice. So now let's put all of this together. I have a 0 minus 1 minus 0. So that's a negative 1. 1 minus 0 minus 1 should be 0. 2 minus 1 minus 0 is 1. 1 minus 0 minus 1 will be 0. Okay, so this here is my v3. Now, just like before, if you want to do a sanity check, the inner product of v1 and v3 should be 0, and the inner product of v2 and v3 better be 0. That was the whole reason we chose these three, is that I want to make sure that this inner product is 0, this inner product is 0, and this inner product is 0. Okay, so that's our step number 1. Right, so now we've constructed this orthogonal basis here, S prime. I still have to do the second step, which is find an orthonormal basis. So we have to normalize. So second, we normalize to find our S double prime. So this actually is not very difficult. So for u1, of course, I have to take the inner product of v1 with itself and then just divide by the square root. So over here, v1, we said was 1, 0, 1, 0, v1, 1, 0, 1, 0. So let's write this here. And then if I want the inner product with itself, I just take sums of squares. And of course, I really want the square root of that. So if we stare at this here, this is just the square root of 2. Right. So that is our u1. u2, very similar. Here I'll just take v2, but I have to normalize. right? So just 1 over the square root. So for v2, over here, this was 0, 1, 0, 1. And then we'll just take the norm, and we'll take 1 over the square root of that norm. Right? Just say really just 1 over the norm. And here, we get 1 over the square root of 2 times v2. Okay. And a similar expression here for u3. So we just have to take v3 and then just divide by its norm. So v3 we said here was minus 1, 0, 1, 0. So it looks very similar to v1. So again, minus 1, 0, 1, 0. Then now we just take the sums of the squares. And we'll take 1 over the square root of that. And of course, that's just 1 over the square root of 2. Minus 1, 0, 1, 0. Right. So putting all of this together, we conclude that an orthonormal basis for W is this set that I'm calling here S double prime that just consists of these 3 vectors. So 1 over square root of 2, 1, 0, 1, 0, 1 over the square root of 2, 0, 1, 0, 1, and then finally 1 over the square root of 2, minus 1, 0, 1, 0. Okay, thanks for listening. So I hope that this lesson makes sense.